Welcome back. In today's video, we shall look at the physics behind the motion of a yo-yo. A yo-yo is basically a construction that consists of a disc like that is being wrapped around by a string. As the disc is released, it will start to rotate in that direction about an axis that is passing through the middle of it, which is the center of mass. So the axis is coming out of the board. It will start to rotate with some angular speed, omega, and at the same time descends downward with some acceleration and with some linear speed, v. It will continue to descend under the influence of its own weight and also the tension in the string, in addition to the torque that is provided by that tension that is causing it to spin. And this movement will occur until it gets to some lowest point, and then it's going to go up to a certain height and then will descend again and on and on. What we are interested in this video is the physics behind such a motion. We shall look at the force or forces that are acting on the system in addition to energies. Let's look at the force aspect of the system. Before we can understand this, we have to create a free body diagram. A free body diagram is a diagram that lists all the forces that's acting on the system. The first one is, of course, the weight, m being the mass and g being the gravitational acceleration. And the second force is, of course, the tension in the string. We note that this weight acts through the point, which is the center of mass of that disk. The axis of rotation passes through that center of mass and perpendicular to the plane. We understand that this is a rotational motion about the center of mass, or about an axis passing through the center of mass with some angular speed, omega, and angular acceleration, alpha. That means that must be also a tangential speed and tangential acceleration, v and a, respectively. So let's write down Newton's second law for this system. The net force that is acting on this disk is downward, because the movement is after all downward. So that means the weight minus the upward tension is the net force. And that net force, according to Newton's second law, must be the same as mass times that linear acceleration. At this point, we should note that the acceleration is the acceleration of that center of mass, denoted by the subscript cm. In addition to that, there is a torque in play. After all, there is rotation, so that rotation must be created by some kind of torque. After all, this disk is rotating with an angular acceleration alpha. So Newton's second law for rotation states the net torque acting on this disk equals the moment of inertia of that disk about that center of mass times the angular acceleration. We also know torque is created by some kind of force. Now there are only two forces. One is the tension, the other one is the weight. We note that the weight acts through the center of mass, so it's passing through the axis of rotation. That means it creates no torque for such a rotation. And the reason, or the mathematical reason, the distance between that weight and the axis of rotation, the one we call r in that expression r cross f for torque, is 0. So there is no torque created by that weight. That leaves us with tension. You see the tension is going up, and the perpendicular distance is the radius of that disk. Let's call that radius r. What is the direction of that torque created by the tension? That r vector is going leftward. The force, in this case the tension, is going upward. So when you use your right hand fingers and you curl from r to the force, in this case T, your right hand thumb is going into the board. So that is the direction of this torque created by this tension. We note that if the torque is going into the board, the angular acceleration must also go into the board. And since it is in a clockwise direction and it is speeding up as it's going down, we see that the direction of the alpha, the angular acceleration, is also going into the board according to our earlier sign conventions. So they agree. So let's write down expression for the torque. It is tension times radius. The angle between them is 90 degrees, so sine 90 is 1, so you don't have any other things besides t and r. The right hand side, the moment of inertia of that disk about that an axis passing through the center of mass, times the angular acceleration. And that's it. Well, this is the torque equation. At this point, we should note that you can relate the acceleration of the center of mass to the angular acceleration of that disk. The acceleration of the center of mass is tangential in nature, so that tangential acceleration equals the radius of that disk times angular acceleration. Likewise, the tangential speed at any point equals the radius of that disk times the angular speed. The next concept is the energy concept. Let's assume the yo-yo starts from some initial position and then it goes down all the way to the final position. And the distance is L. L is, in other words, is just the length of that string before it goes back up again. So we know energy is conserved. That means the mechanical energy at the initial point must be the same as the total mechanical energy at the final point. So mechanical energy consists of two things. One is the gravitational potential energy plus the kinetic energy of that yo-yo. So the sum of these two energies at the initial point must be the same as the sum at the final point. As simple as that. This is the statement of conservation of mechanical energy. These are the main physics behind the motion of a yo-yo. Of course, we are ignoring things like the air resistance. So we are just looking at an ideal case here. Let's look at the following problem. A yo-yo has a moment of inertia of 1000 grams meters squared and a mass of 150 grams. Its axial radius is 4 millimeters and its string is 150 cm in length. So it rolls from rest down to the end of the string. Find the magnitude of its linear acceleration and the tension in the string. So let's do part A. As we have discussed earlier, the two forces are tension and the weight, mg. That's going down with the linear acceleration or the acceleration of the center of mass, ACM. And because it's also rotating, there is a torque involved with an angular acceleration alpha. So Newton's second law states mg minus tension is MACM. So that's equation 1. Newton's second law for rotation, as we have just explained, states the torque due to that tension equals the moment of inertia of that wheel, which we know to be 1000, times the angular acceleration. However, the torque is given as the product of that tension times the radius of that wheel. Let's call it capital R, and that equals I, and alpha can be written as the tangential acceleration over the radius of that wheel. So ACM over R. So that's equation 2. If we use equation 2 to express tension in terms of other terms, you get I times ACM over R squared. And when you take this expression, you put it in equation 1, you get mg minus I ACM over R squared equals MACM. And you can write down the expression for the acceleration as quite simply mg over m plus I over R squared. So let's put in the numbers to determine the acceleration. So the acceleration is, the mass is 0.15 kg. I'm converting grams into kg. G is 9.81. Again, 0.15 plus the moment of inertia. Moment of inertia is 1000 grams cm squared. Changing the grams into kg, you get 1 kg. And 1 cm is 10 to the power minus 2. So cm squared is 10 to the power minus 4. So that is the moment of inertia in kg meters squared over r squared. R is 4 millimeters, so 4 times 10 to the power minus 3, converting that into meter square. And calculating, you get 0.23 meter per second squared for the acceleration. Having found the acceleration, we can get the tension from this equation. Again, moment of inertia is 10 to the power minus 4 kg meters squared. Acceleration is 0.23. We have just found that. Over radius squared, radius is 4 millimeters, so 4 times 10 to the power minus 3 squared. And that's going to give you 1.44 newtons for the tension. Now let's do part B, time it takes to get to the end of that string. Now this you can solve using kinematics. So L equals half times the acceleration t squared plus the initial speed, because it is starting from rest, that is 0, t. So that term goes away. This is the kinematics equation. So the length is 1.5 meter. Half the acceleration is 0.23 t squared. And you can find the time. And you get 3.61 seconds. So part B, 3.61 seconds. Part C, at the end of that string, what is the linear speed? Of course, we can use kinematics again to do this. U is 0 because it's starting from rest. Acceleration is 0.23. Time we have figured out, 3.61. That's in part B. And the answer is 0.83 meter per second. Part D, what about this angular speed? Angular speed omega equals the linear speed we have determined in part C over the radius. So 0.83, and the radius is 4 millimeters, so 4 times 10 to the power minus 3 meter. And that's going to be 207.5 radian per second. Part E, translational kinetic energy. Translational kinetic energy is half times mass times square of that speed at that end of the string. Now the mass of that yo-yo is 150 grams, so 0.15 kg. V is from part C, 0.83, square that, and you're going to get 0.052 joules. And finally, the rotational kinetic energy. So half times the moment of inertia times the square of the angular speed. The moment of inertia in SI unit is 10 to the power minus 4 kg meters squared. Omega has been determined in part D to be 207.5. Don't forget to square it. And the answer is 2.153 joules. You see, the total kinetic energy is about 2.21 joules. And it should match the gravitational potential energy at the highest point, because all the gravitational potential energy is converted to the total kinetic energy by the time the yo-yo gets to that lowest point. So let's see if that is true. The gravitational potential energy at the highest point, assuming that this point is 0 joules, is the mass, which is 0.15 kg times gravity, times the length of the string, which is 1.5 cm, and you see you'll get 2.21 joule as well, which is none other than the principle of conservation of mechanical energy. As always, thank you for watching.